Okay, welcome to this next section. So before I start, I've got a small favor. My mother is 84 years old this year, and she has no idea what I do for a living. So if I could get you to all wave and say, hello, Mum, I can take a panorama picture and show her all the new friends I've just made. Are you up for that? Yes, okay, right, I'll start over here. Are you ready? 1, 2, 3, go. Hello, Mum. All right, you guys are awesome. Okay, I am going to talk to you about Redis data structures. And the intention is to talk to you about Redis data structures for non-Redis people. So how many of you use Redis on a daily basis right now? A smatter. How many use a relational database? A whole bunch of you. How many of you use a document database? A bunch of you as well. Okay, so I think we've got a good smattering of audience. So I am going to talk about data structures in Redis, transactions, how to think and approach Redis, and some random conclusions. Now, as you can tell by my accent, I didn't grow up in the United States. I grew up in this strange place called Britain, which is a small island in the middle of this very great ocean. And, you know, I really did grow up eating things called spotted dick. This is a great dessert. We had custard that came in a powder form out of a can. We drove on clearly the wrong side of the road, but there's several people in blue who agree with us, you know, most notably the Australians and Indians. Go on, guys. And I learned how to translate things from phrases I knew that had a very different connotation when I came to my new country of America. And so I think the lesson of this is we have to learn to adapt and change over time. Oops. So you may have grown up with class diagrams or ER diagrams, and we have events and tickets in this model, or maybe XML, or if you're one of the cool kids, maybe you spend all your time in JSON. But all of these are just different ways of representing the same basic business domain objects that we want to manipulate. They're just different representations. So how is Redis different? As you probably already know or been in several other talks, Redis is a multi-model key store. And this means that we have a set of commands that operate on those keys. But some commands operate on specific types of keys, and then those commands can only operate on specific values within those keys. Right? I can increment an integer, but it makes no sense to increment a string. And so we have to first think about that, and then we have to think about the data type can change over time. This key may start off with a string value, but you could then put a list in there, you could put a set in there. And so Redis naturally supports polymorphism. If you've come from the land of fixed schemas, this is very odd the first time this happens to you, when you go put in a value and moments later you read it out and somebody has changed it to something else. And so you're in this world where data structures are fluid and dynamic. And there's some really good things about that, but there are also some things you have to think about. So let's start at the beginning. So on the left, we've got a key. The key's got a name. Here it's event:judo. And then it's got a value of sold out. And then that value could be one of a number of data types: a string, a list, a set, a sorted set, a hash. These are just some of the basic ones. There's a whole variety of other data structures that Redis supports, but let's stick with the simple ones to begin with. So let's start off with the key. So obviously a key's got to be unique. It can be up to 512 megabytes in size. We really wouldn't recommend you having a 512 megabyte key name. You can do it. I really wouldn't recommend it. They're binary safe. That means that we do a binary comparison. We're not comparing strings. We're comparing bytes to see whether we have a key match. So that's keys. So what do you do about your key naming, right? So keys themselves are got to be unique in a global space. So how do you ensure that your key names are unique? Well, often people will build a structured name into those key names. For example, you see here, we've got a domain object of event, and then we've got an instance of event of judo and venues. right? So people have, the typical convention in the community is to use colons or some other separator between the parts of these key names. You know, people sometimes use plurals for lists or collections because it makes sense for a plural name to be many things. But you also have to bear in mind that, as I said, the key names are binary safe. So you see these last three examples of event, fencing, and fencing and fencing. Well, they are all three different keys, right? Because Redis is not doing a case-insensitive match, it's doing a binary comparison. And all three of those keys are three separate keys. So the key thing here is to have a naming convention and stick to it, because this will help you throughout the life cycle of your microservice or your application. Especially when you start having data co-located from different services in the same Redis instance. If you've got a consistent naming convention, then you're likely to not have clashes. Now, the cool thing about keys is I can make them expire, I can make them vanish. And who loves vanishing data? Well, there's lots of great use cases where you want your data to vanish. Perhaps you've got a session store where you only want to keep those active users. And so in Redis, I can automatically set an expiration time for a key. So we can see in this first example, I've set an expiration time of 50 seconds. And so what Redis guarantees is that key is around for at least 50 seconds, and sometime after 50 seconds, it's going to be automatically removed from the system. So if you've got data that you periodically want to retain and then purge, you can automatically set the expiration up in Redis. You don't have to have a separate thread that goes and cleans up the data for you. So when you first create the key, you can set an expiration. You can set the expiration for an existing key, but you can also remove the expiration for an existing key. So you can change your mind. It's not something that you define once. You can constantly be changing and updating it. So if you think about a session store, somebody might come in and log into your website. You've stored the session cookie and information. You set the expiration for 5 minutes. And let's say they do another web request. Well, you can reset that expiration for another 5 minutes and keep on going until they stop interacting with the system, and then that object will naturally get decayed out of the system for you automatically. Okay, so we've now got a key and we can put a data value in there. So I've got 3 examples here of putting sold out 42 and 3.14159. No, 3.14159, yes. So the key thing about Redis is it allows for polymorphism. Things can change over time. It's also schemaless. So you can see that in this first example, I set the key to sold out. Internally, Redis has said, oh, that looks like a string, so it's going to store the encoding as an Ember string. I later then set it to 42. Well, 42 looks like a string as well, but Redis has a look at that value and says, I think that's an integer. And so it stores the internal encoding as integer. So Redis is always looking at the value that you're putting into that key to figuring out what it is, because that will then govern what you can do with it. So if we look at doing something, we're going to take our first command, which is doing an increment of this key called event fencing. All right, so if we look at the value, it's got a value of 42, its data type is string, and so the increment command operates against string data types, so that's good. And then the encoding is an integer, so an increment can increment an integer, so that's a valid thing to do. Now, in this later example, we've got event judo, which has got a string of sold out. So it's a string, so it's the right data type, but an increment can't increment a string, right? So the command cannot execute because the value inside the string is actually a number. Equally, if I try to increment another data type like a list, then it's going to fail because it's the wrong data type. So when you start using Redis, you create these data structures, and then you've got commands that can be applied to those data structures, but whether that command can execute is going to be dependent on what is the type of value inside that structure. So again, this is something that you are constantly thinking about as you're using Redis. So one of the collection data types in Redis is a list. So lists are pretty cool. They're a doubly linked list. So I can see here I've got judo, fencing, and taekwondo, and I can traverse the list in either direction. Normally you would call judo the head of the list and taekwondo maybe the tail of the list. In Redis naming conventions, judo is the left and taekwondo is on the right. So you'll see commands that start with lpop or rpop to denote which end of the list you're going from, the left or the right. So you can see here an example. I can do an lpop of events, and that's taking this element from the left of the list and removing it from the list. Equally, I can do the same from the right. So you have to get used to the fact that in Redis, lists have a left or a right-hand side, not a head or a tail. And you'll see this in the name of the commands and in the documentation. So why are lists really cool? Well, you can use lists to create a whole bunch of things, from queues and stacks. Lists have also got the ability to have a variant called a cap list. So you can ensure that only a certain number of elements are retained. So a great use of a cap list is, for example, you want to keep the last 5 posts on an activity stream. As a new post comes in, you then trim that list back to 5 elements just to keep the latest 5. So cap lists are a great thing to do. One of the reasons lists get used frequently within Redis is that their time complexity is O1, right? So we're not going to dive into big O notation, but if you look at each command inside Redis, the time complexity or how difficult it is to execute that command is documented. And so what O1 is saying is that the time to manipulate the first element in the list is always a fixed time, right? Irregardless of how big that list is. So to go get the first or the last element, it doesn't matter whether that list is 3 elements long or that list is 1 billion elements long. And so successful use of Redis is all about using these commands efficiently. If I'm always accessing the head or the tail, I know the time complexity is O1, and therefore it's going to be very, very consistent irregardless of the size of that list. So many of the commands and lists are all O1, from popping and pushing, from doing a block put, and so on and so forth. So they're really great for doing things like inter-process communication, things like activity streams, and so on and so forth. All right, sets. So sets are an unordered collection of unique values. And so you probably saw in the keynote this morning, a set could be used for recording unique words or unique tags. Let's say I'm tagging objects, I can create sets of all the unique tags that I've ever seen. So we can see here we've got a set with 3 elements, and I can find the members of those elements. I can do a S members events, and I can see judo, taekwondo, and fencing. And so one of the things that sets allow you to do is perform set operations. So you can do a difference, an intersect, and a union between other sets. So, for example, if you were creating a taxonomy of tags associated with objects, for each object I have its unique tags, and then I can do an intersection between those sets to find out the union of all tags or the differences of tags between 2 objects. And so these set operations allow you to start building some very powerful constructs. A variant, so before we do that, why are sets cool? Well, the set operations. As I said, typical use cases are things like tag clouds, finding unique visitors to your website during a period of time. You just put their cookie ID in and you can see each one of those unique visitors and record that in a set. Again, many of the operations are O1, which means they are consistent irregardless of the size of the set. And so this gives you very consistent performance as you are using and manipulating those data structures. A variant of sets is a sorted set. And unremarkably, this is an ordered collection of unique strings. And so when you add a value into a sorted set, what you do is you specify a score. And all a score is a floating point number. So you specify the value you want to store and the floating point number, and that floating point number governs the order of the elements in that set. So let's pick a really simple example of how you would use that. So imagine you've got a leaderboard in a game. So the value is probably the player's screen name. The score is their points total or other metric you want to evaluate that leaderboard by. So as you update their score, that set is going to automatically be reordered, and when you go and obtain that set, you get that set in the correct order, either from highest to lowest or lowest to highest. So again, sorted sets provide set operations like union and intersect. And you can manipulate these sets through position, by value, by score, and so on and so forth. So they provide a great deal of flexibility. As we said, what are the typical use cases? It's things like leaderboards and a priority queue. So you can imagine if you're doing a queuing model, you may want to have streams in that queue with different priorities. You can use the score to provide the priority, and therefore, as you pop elements off that queue, you can do it on a priority basis. Again, the operations are mostly a very simple time complexity of O1 or O log n, and that means that you can perform these operations and they provide a consistent performance regardless of the size of the sorted set. Okay. Finally, hashes. So the easiest way I think about to think of a hash is it's a mini key value store within a key. So I've got a key here of event judo, and within that I've got pairs of fields and values, venue of Superdome, capacity of 32,000, subway, it's on the subway line. So you can store these, essentially this single level of hierarchy of values within a key. You can add and remove those fields dynamically. So I've got 3 fields in there at the moment. I can add another 2 fields now, and 5 minutes later I can remove one of those fields. And so hashes are a great way to consume something like a data feed, where that data feed may be changing each time you make a call request. It may be an IoT device that is sending you specific attributes, and you can actually take those set of attributes and store that within a hash, and you've got that complete representation. You don't have to define the fields up front. It's dynamic. So you don't have to go through the sort of traditional create table process in order to alter those fields that you're storing. So why a hash is cool, again, a lot of the operations are O1. So that means that accessing a field in a hash with one field is the same cost of accessing a field with a hash with 1 million fields in it, right? So the performance is consistent irregardless of the size of those hashes. Typical use cases, things like rate limiting. I want to keep a set of counters, for example, on an API endpoint, and I only want to ensure that during a given period of time that there's a limit of number of requests that I'll accept. Each time I see a request, I decrement that counter until I get to 0, and I no longer accept requests until the next time period starts. So rate limiting is a great one. A session cache. You can imagine taking your cache object and instead of storing it as a binary string, actually normalizing those fields out into the hash and then be able to store and access those fields. Okay. Are you all still with me? Sort of. Okay. You know, the first time you come to a system like Redis, especially if you come from a relational database system, you do feel that somebody has run off with your firstborn child and is asking you for a great deal of money for their safe return. But trust me, they will safely return. So let's put that into practice. We've got a real simple schema here. we've got an event, and we've got a ticket tier, and the intersection of that is the particular ticket tier for this event. Right, so I'm going to say, look, I've got the judo event, and perhaps I've got a VIP ticket, and I've got a gold ticket and a silver ticket. So in JSON, you would probably do this through a technique called embedding, whereby you can see the first level attributes, and then we have this element called available, and within inside that document, we've got another document that describes the general tickets, and then within that, there's another document that describes quantity and price. And so in JSON, you could represent this data in this hierarchical form of embedding and embedding. If you're more used to tables and foreign keys, on the right-hand side is a class diagram, but you can see how that could easily translate into a normalized relational schema with tables and foreign keys. So how should we model this in Redis? Well, before we think about that, we've also got to think about the associations, cardinality, and containment, right? So I won't read through this, but what this diagram is saying is for a given event, there may be 0 or more tiers of tickets available, okay? But also, it's also saying when I delete the event, I want to delete all those ticket tiers as well. In a relational database, that would be a delete cascade relationship. In JSON, because you've embedded, you delete the JSON document, everything within that document gets deleted as well. So you've got to think about the cardinality of those relationships, but also those containment rules. So what is the way that typically people would first store that object in Redis? Well, what they would do is they take the whole object as a string, and they would encode that whole string and store it in Redis as a single string. As you can see here, there's a ton of horribly escaped quotes because you're storing a string within a string. That means you've got to escape all the quotes and all that other garbage. Now, why do people go down this route? It's super, super simple. I can serialize my object into a string and then just squirt it into Redis, and then I'm done. And if I want to get the object back, I can just get that whole string back and deserialize the string. The problem comes is if I now want to manipulate or change that field, right? I've got a quantity of tickets. Let's say I've now sold 5 tickets. What do I have to do? I have to take this binary object that I've stored in Redis, take the whole thing back through the network, deserialize that on my client side, manipulate that field by decrementing the value, then turn it all back into a big string, transport that through the network, and store it again. Right, so if you want to make partial changes, then you take the cost of transporting that whole object backwards and forwards and deserializing and serializing it. So what is the sort of typical recommendation in this case? Well, there's a couple of choices here. One of the things you can do is simply flatten out that structure. And so as we saw with key names, a field name can have a structure to it. So you can see here we've got available, :general, :quantity. Right, so what in effect we've done is we've flattened that JSON structure, or those foreign key relationships, into a single flat object, and we've used the field names to essentially show that those relationships. So we can now flatten the whole object. And so this now gives me the ability to get and set individual fields within that object without having to materialize the whole object across the network. So this can be a more efficient solution if you need to manipulate the fields within that hash. A sort of variation of this is, so the good thing about hash, before I look at the variation, is you get really great atomic updates and deletes. You can do a set on a single field, right? And that's a single atomic operation. The bad is you could end up with an enormous object, an enormous hash. And so there's a decision point you can make about how far you flatten, how many of those containment relationships I want to traverse in order to draw the boundary around this one particular hash. And so, you know, normalized version of this would be you create a hash for each one of those objects. And then you can create a set to store the relationship ends. So as you can see here, we've got the event with all of those first level attributes. We then create a hash for the general ticket tier with the quantity and price. And then we add a set where we add in that particular relationship end to that set. So if you want to sort of more normalize the objects and separate them out, you can. You could argue you don't need to store the set. The set is already implied by the naming of our keys in the first place. Because I've named the general ticket tier is essentially the key name for the event, then I've just added in the ticket tier name. So you don't even need to store the sorted set or the regular set in this case. What you could choose to do is store it, and then that gives you the ability to now find all those associated hashes by just traversing that list. So this sort of comes down to knowing how your data is going to be accessed. If you want to always find out those associations, then storing the associations in a set may be really useful. If you never need to traverse those associations, you can just do it implicitly through the key naming convention. Okay, so what's good? You've got a very extensible structure. These hashes are independently stored, which means that you can distribute them across clusters. Clearly, the bad thing you'd have to do here is you have to maintain these relationships. You're now responsible for maintaining those relationships. Okay, so now are we cool? Now that we've now separated our concerns into multiple hashes or multiple lists, how do we make sure that I do a consistent write, right? You're thinking about your business domain object. To make this, use case or this microservice execute, perhaps you're touching 4 or 5 of these elements, and you need to know or need to guarantee that you've made a consistent change. So Redis has transactions. Is this a surprise to people? Sort of. No. Okay, so what Redis can do, as we can see on the right-hand side, you start a transaction with the multi-command. We then can do a number of operations. I'm doing a set and I'm doing an increment, and then I do an execute. And so what Redis is doing is it's storing up all of those commands, and then when it gets to the exec, it executes all of those commands as one single atomic block. Right, so you're guaranteed that that block executes or doesn't execute. Equally, I can start a transaction and decide that I don't want that transaction to proceed, and I can use the discard. So we can have a look at that in action. As you can see, we've got time going from top to bottom. I've got 2 clients. The first client does a get. The first client then starts a transaction. It does an increment. And as you can see here, client 2, when it does a get, it's seeing the value of that key independent of those changes that the other client is making a transaction. Redis is not applying those commands. It will only apply them when it gets to the exec, right? So for every other client in the system, what's happening in that transaction is isolated from all of the other interactions the other clients have got, as you'd expect. So finally, when this transaction executes, it does the increment and it can do its get. And so the context of that execute is where all of those operations now execute. And that's the values they will see. So if we look at this slightly differently, I've got client number 1 starts a transaction, it increments my key. In another client, I decrement the key. Right? And so the second client, when it does a get, it sees the current value, because the first client is simply queuing up those items. Those items aren't being executed. They only get executed when the exec command is run. And so this means that you're getting, each one of these clients is seeing an isolated view of the data, even if the keys are being changed by both clients at the same time, depending on whether one's doing an immediate change or one's doing a deferred change through a transaction. So Redis also supports optimistic concurrency. So I can put a watch on a key. Here I'm putting a watch on the judo event, and then I'm going to make some other changes to those keys. Another client can go and make a change to that. And what that'll do is when I come to execute that transaction, because Redis knows that key has changed, it fails the whole transaction for you. So this means you can build in the logic that I can do an optimistic, essentially optimistic concurrency by reading the object, making the changes, and when I come to write those changes, I've got a guarantee that if somebody else has changed, my transaction will now fail. Okay, why are they important? As we saw, what you end up doing is splitting your data across many different data structures to represent parts of your domain object. And as a consequence, you may have the need to touch many parts of those keys in order to successfully complete that business transaction on that business object, right? And so the combination of optimistic concurrency control and transactions allow you to give those guarantees to the objects that you are manipulating from a business or a domain perspective rather than from a data structure perspective. All right, so we're really cool now. I really wish I could have a haircut like this, but the days of having haircuts like that are regrettably long since passed for me. So there's some other great things you can do. Redis supports geospatial. So I can add a geospatial point. So I've got a latitude and longitude point, but I can also name it. It's not just a point, it's a name point. So at those coordinates is Nippon Budokan. Which now allows me to do several things. I can do a geo-radius. I can say, tell me all the other named points that are within 25 kilometers of this particular point. It could be 25 feet, 25 miles. You can specify the type of unit as well. And so that's going to return me everything within that radius. I can also do radius by member, so I can say, show me everything that's within 1,500 meters of Nippon Budokan. So you don't have to do it just by point, you can do it by the object's names in their own right. And so that will give me a proximity search like that. I can also do the geo-distance between two named points. So here we're doing the distance between Nippon Budokan and Makari Messe. So happens to be 26 point something or other kilometers. So this means that you can now use all the great assets of Redis, which is high throughput, it's memory-based, but also be able to do that for geolocation or geospatial data. So you can use that for everything from sort of ad tech, social, logistics, what's near me, which friends are close by, or what adverts should be placed on this user given their proximity or their direction of travel. So that's geospatial. The other popular feature in Redis is publish and subscribe. So this allows you to create a topic, push messages to those topics, and have other clients subscribe to that topic to see those messages come through. So we've got a simple example here of publishing and subscribing to those messages. And so it's very easy to see how you can then use this as a form of what I would describe as unreliable message delivery between system components. And so you can see we're publishing a message, and as the new client comes on, the new client will see all the messages that are published after it subscribes. So it's only going to see this new event. It's not going to see the preceding events, for example. So why is it cool? As I said, inter-process communication. So, some conclusions. Data modeling is different in Redis, especially if you've come from highly normalized, highly relational schemas. If you've been using things like JSON or XML, then you're probably more familiar with the fact that you're dealing with data values that can change their structure and type over time. But in order to successfully use Redis, you really have to know what is your use case and what are the operations that you need and those API calls in order to satisfy the needs of the requirement. Should I use a list, a set, or a sorted set? Well, it really depends on how I want to access that data. You also want to look at the data cardinality and the data distribution. As I said, lists are extraordinarily efficient at getting the head and the tail of the list. But in any linked list, trying to access elements in the middle or scanning a list is inefficient. And so knowing your access patterns and your data cardinality allows you to choose a list versus a sorted set to solve your problem. And once you know those, you can better select your data structure. Some things you'll need to think about is, as we said at the beginning, Redis has got a flat naming structure, right? So if you put your key in as 1, 2, 3, then that's the only key 1, 2, 3 that can exist. And so the community convention is to have a structured naming convention for these keys that indicate your domain object, the ID of that object within the domain, and so on and so forth. As I said, transactions allow for atomic operations and enable safe multi-key writes. And this is important as you start separating concerns across different data structures. And when you come to deal with relationships, then you've got a couple of ways that you can flatten those. You can flatten them into single very large hashes, or you can flatten them into multiple hashes. And if you want to have information about the relationships, you can store those in sets. Okay, there are a ton of things we didn't talk about. Hyperlog log is another data type which is great for probabilistic counting structures. It will give you a rough approximation of how many elements are in the structure. So if you want to know there's about 5,000 people subscribed, then it's a great structure for that. If you need to know it's 5,048 precisely, then a hyperlog log is only going to give you an approximation, not an exact number. Redis has the concept of bit fields. And so you can store bits inside a Redis data structure. So for example, if I was doing a seat reservation, I could store a bit structure that describes which seat is available and not available. And I can store that in a very compact way inside Redis. So it's a great way of doing either things like bit fields like that, or maybe counters for time series. You've got 24 hours, therefore you've got 24 16-bit values that you can store in a single key and then increment parts of that value in order to get your histogram over time. So it's great for doing really compact structures. Redis is also extensible. As you probably saw this morning from the keynote, there's Graph, there is ReadJSON, there's Redisearch. So there's a number of ways to look at very different types of data structures in order to solve your problem. There's a session, I think later today or tomorrow, about how you build your own module so to support your own particular domain-specific data type if you need to go down that path. So extensibility is a key thing. And finally, a shameless plug. Yes, this morning we launched Redis University. The first course starts in June. You can enroll now. And it is a 6-week course that will dive into Redis data structures. And it will tell you all about the ins and outs of how you choose particular data structures. And part of the course is building a reservation system for the 2020 Redis Games. Because I can't call it the Olympic Games because that's trademark. So the 2020 Redis Games is what we're building the application for. So it's a free online course. You can sign up at university.redislabs.com. Or you can come down and talk to me on booth number 10 downstairs if you want to have a chat. And that's what I've got for you.
Are there any questions for Alvin?
Hi. You mentioned there's limits for the keys. Is there any limits for the values?
So yeah, the question was, is there a limit to the value size? So I said the key size is up to 512 megabytes. For strings, that limit is also 512 megabytes. Equally, there are other size limits for the other data types. So some of them are, like lists can be essentially infinite size because it's just linked lists. Other of those structures have other size limits.
I overheard that you cannot use keys in production. Someone Taig had said that several times, and I really don't know what else you would use in production. It's just something that kind of baffled me. So I was wondering if you could speak a little bit to that.
Sure. So the question is, should I use keys in production? Okay, so keys is a command. And the keys command, you say keys, and then you can specify a wildcard. And essentially what that will do is that will return all the matching keys. So let's say I've got a Redis instance with 1 billion keys in it. And I do keys space asterisk or star. What that is it's going to be a blocking command. So Redis will now start queuing up any other commands that are coming behind. It's going to find all of the keys in the system, which we said was 1 billion. Then it's going to aggregate that response and then send the response to the client before it can start processing the next request. And so that's kind of why you'll hear several people say don't use keys in production, because it's a blocking command, and if you've got a very large amount of data, you stop all the other commands executing. Now, is keys a great command? In dev and test, it's awesome because you can go find things and it's a great development and debugging. It's just one of those commands that you have to think about your context before you execute it, because you're in production, you do keys star, and you go, oops, as all of your alarms start going off because everything's now backed off.
You mentioned strings. Are Unicode handled correctly?
Sorry, I couldn't quite hear you.
You mentioned strings as one of the data types. How about Unicode? Are Unicode strings separate?
So the question is, what about strings in Unicode? So strings in Redis essentially just a binary stream of values. And so you can actually store text data, you can store binary data, you can store floats, integers. It's just a stream of bytes, and that's how Redis interprets it. I'm sorry, I can't hear you without the microphone.
Are there anything to be noticed for search capabilities in Unicode? Too much echo if I keep it too close. Are the search capabilities, will they work correctly with Unicode strings? Text search you mentioned as one of the modules.
Yeah, so there are some string manipulation functions, yes, and they'll work on those correctly. All right, I think there's a question at the back here.
Sorry, I'll get
Make you do the running. This is how I get you your exercise, Marco.
From a design perspective, if you have, you're using keys and you have keys that expires and keys that don't expire. So do you separate the two? And if you are, what are the performance? I mean, I'm thinking of the underlying, like how do you store that in terms, so the performance, how would that, what would be your suggestion?
Yes, so the question is, how do keys that expire and keys that don't expire coexist, right? So Redis has a single flat namespace. There are a bunch of keys. At any point, any of those keys could have an expiration on them, but those keys could have an expiration, then the expiration removed, right? So what Redis is doing behind is it's doing some sampling and scanning to understand which keys are about to expire. And then it will then queue those up for expiration when that time exceeds. So when you set an expiration, that is a guarantee of the minimum amount of time the key will exist. It's not a guarantee that it will expire at exactly that point in time. It will expire after that point in time, and usually a very short period after that time, but it's not a guarantee at 50 seconds precisely that key expires.
keys that expired and you have keys that, in a structure level, is there going to be a performance in terms of like read?
Yeah, so the question was, what about the performance? So what Redis is doing is in the background, it's got essentially a reaping thread that's going through, clearing up all of those keys that have expired, right? It has to in order to give the memory back to the system. So yes, there is a cost associated with that, but if you think about all of the early use cases for Redis were caching, and so it's a very highly optimized and tuned part of the system because if you were building a session cache with Redis, which is all the traditional use cases, you'd want that to be done very, very efficiently, and it does it efficiently.
So I wanted to follow up on the Unicode question. So in one of the examples, you gave JSON as something that Redis can deal with, and the default encoding for JSON is UTF-8. So if I write a UTF-8 JSON document with non-ASCII characters and then read it back from Redis, will that properly be round-tripped?
Yeah, I mean, the key thing is that let's say you've got this JSON or a Python dictionary or a Java hash. What you've got to do is you've got to serialize this into a binary stream for Redis. Redis will store that binary stream and it will return you that binary stream. So what you're really dependent on is the code that is going to do the serialization and deserialization deals with that case correctly. Once it gets to Redis, it's just a binary stream. We're not interpreting, we're just storing those bytes.
Because I looked at the Python binding to Redis, and it wasn't really clear that this is going on. So, I mean, does Redis Lab maintain that library? Because that should be clarified, because that's important.
The Python, so the question is who maintains the Python driver and is that documented? So the Python driver is maintained by the community, and in somewhere deep in that documentation it describes that behavior. Now, if you want to store JSON, you've got multitude of options. You don't have to store it as a binary string. You can store it as a hash. You can also store it with read JSON if you're using one of the modules. So I'm happy to dive into that a little after this if we have some extra time.
Can I use like Chinese characters as keys for Redis?
Okay. Yeah, it should be fine. It's a binary string. It's binary safe. Okay, I think we're out of time. So I'd like to thank you for your time. If you want to